In this part, we're going to look at mostly attachment systems of glass. One, the idea of a spider attachment system to any kind of a structure, and then we'll look a little bit at these systems when they're played out into cable systems. Before we get into that, though, I had a couple of slides that I thought were interesting. So this is Tammany Hall, and this was just recently in the news, at least last year it was, and this is hyperlinked to the article about it. It's a refurbishment of Tammany Hall, and I thought it was noteworthy because here we have a historic building with a parametric, very modern kind of attachment to it. So it could be that you're working for a firm that you think may not use these kind of advanced techniques because it's really oriented towards historic facades, and yet again, progressive firms are always pushing boundaries, and so here we have a traditional building with a really quite an advanced high-tech skin based on some of the ideas of computational design that we're currently working with. And that goes back to the work we did last week with image mapping. So here we have an example that I thought was quite neat of just a subtle use of that image mapping technique for a feature wall inside of a building, where we've applied some kind of data to create a three-dimensional pattern onto a wall and cut it out of, I believe this looks like it's stone. So now on to this idea of attachment components. And before we get too far into it, the segue here is kind of like from our last talk about how powerful silicone is for adhering our glass and holding it. And when we start to talk about these spider systems, one of the most recent advancement is the ability to adhere the glass just with this amount of cylindrical area, tying it back to the spider. And that may not seem very significant to you now, but as we go through this presentation, you'll see how much has to be done to that glass assembly in order to accommodate the conventional way of doing it. And that conventional way is to actually go through the glass. So here we have this white area here is actually the thickness of the glass. This is an elastomer to protect the glass, and you actually cut a hole through the glass to retain it in the spider attachment system. And here we have another example of that. So here we can see a 4-point spider with the attachment and penetrating through the glass to the other side where there's a cap on it. This is also, you can see, as a cable system. And we have this black is silicone between the glazing panels. Here's a close-up of a spider, a typical spider, and so here we have, we can see that elastomer a little clearer. We notice that we have some amount of adjustments here, play back and forth in order to deal with misalignments of the planes coming together. And I had spoken about how this was a problem to cut a hole in the glass for a whole host of reasons. One of the ways you can avoid cutting into the glass is to attach at the edges. So here we have a spider now that's now turned, I think it would be 45 degrees. So now these are working, the glazing is into the groove of the spider assembly. We still have silicone caulking beads, but we've eliminated that idea of cutting holes, and that can be a tremendous advantage. There's probably some other issues that come up with this, the stresses that might be created by attaching at these relatively small points, but I'm not sure that any of them are of concern at our level of design detailing. So here we have a spider moving towards even more advanced techniques. So, and I probably went too fast on this slide. Here we have, we not only have the spider system, but it's also its attachment back to what is a structural glass system here. Actually, it looks like a hybrid system. We have structural glass in one direction, and we have steel cables in the other direction. And I show you these because we're going to actually look later on in this project at modeling some of these ideas. So here we have now what looks like a fully cable-supported spider system or structural system. I put this image in. This is like Alibaba. You can go online and you can find sourcing for these type of materials. Your contractor would do the same. I'm showing you this to be aware that the sourcing of some of these products may be overseas. There may be limitations. Well, there's all kinds of advantage. One could be the custom design of these components. And there's concerns, exploitation of labor, distant labor, or excuse me, distant product sourcing, so that we have lead issues when we're looking at certifying our buildings as being locally sourced, so to speak. This is kind of fun because there's just an idea of this, the massive, I guess, technical issues involved in some of our glass facade systems when we talk about cable systems. And so, obviously this is a cable here and a clamping system to support the glass. But before we get into this, I included this image because of some of the issues that we don't really spend a lot of time in this course talking about, and that's the complexities of modern glazing systems. In this case, we're always talking about light transmission, visible light transmission, and the solar heat gain coefficient, and how much heat can be blocked by the glass. Typically, when we think about passive solar, we really want to get as much heat through the glass in order to warm spaces. But by and large office buildings with heavily glazed surfaces tend to pick up much more solar energy than it can deal with. So the predominance of the methodologies behind their creation and orientation is really to reduce solar heat gain, to keep from overheating our surfaces, our interiors, and needing them to be air conditioned. So we spend a lot of time creating reflective surfaces like low E coatings. Low E coatings allow for visible light to be transmitted, but are really effective at reflecting radiant heat that you can't see, but is in the infrared region. And so there's also concerns maybe is an overstressing the idea of its location, but there are thoughts to which surfaces are coated with these in order to control the appearance of the glass, the visible appearance to the glass to the viewer. And so you can change the way the building looks by where the coating surfaces are applied, where the tinting is, where the air spaces are in the glass, and the type of glass that's used. And always when we talk about thermally high performing glass, we have to have a void space. We fill that with argon because it's inert, but we also have these issues of what happens when we make penetrations in the glass. How do we keep this seal solid, and the complications that come along with aligning up glass that has holes in it. Enough on this one though, but here we can, I guess one more thing is this idea of laminated glass. So we have two pieces of glass laminated together to create extra amounts of structure in the glass. So I want to spend just a few seconds, because I think it's fascinating, about this cable net system that supports this glazing system, because it's so massive. Here we have huge cable systems coming through, and this is a tensioner for one of these cables. And you can see these energy packs are hydraulic systems that are actually built up with pressure in order to pull tension in these cables. And then as they pull tension, the bolt below here is tightened up. So it's a way of putting immense amounts of pressure within the cable system. And here we have just a couple of shots of kind of like the field application of that. So here we have these hydraulic systems pulling the cable down, and then the bolt is then threaded up tight, and then it's moved down and expanded again. And the tensions in these are really quite extreme. And this device on the right-hand side is a way of measuring cable tension. So here we have a cable coming down, and this deflection that is created by putting a hydraulic pressure on it gives an indication of how much tension is in the cable. I put these in because these are out of those presentations. I thought some of this stuff was significant. A free span of the glazing with an L/50 deflection gives you an idea. We've talked about L/120 or L/300, and so these are quite large deflection allowances. Maximum cable deflection of 10 inches under load, under heavy wind load, but this is over a 45-foot span. Still not an insignificant amount of deflection. The cables are, well, you can read these on your own. But just interesting tidbits of fact and ideas about how much pressure, 48,000 pounds of pretension in the cable for the atrium system. Um, and I bring up these ideas of all of this complexity because this looks like such a simple system, but because there is no vertical structure here, it's all cable systems. A lot of tension has to be pulled in order to hold this. I guess we could call it now a membrane, a facade, rigid enough so that it can not break the glass and not cause leaks during deflections. Double skin facades are quite popular still. I've never seen any kind of qualitative information that says double skins perform better than other high performance facade systems. But we seem to have in our psyche the idea that if we create a facade in a facade, kind of put a coat on a coat, so to speak, that we'll get higher building performance. So double facades are still quite popular conceptually and continue to be discussed in the field. They do offer advantages, but sometimes the advantages that we end up finding have nothing to do with what the original intentions of us conceiving of the double facades. For instance, the double facade is to create some sort of barrier, an extra barrier for a better thermal performance. And then typically what is being discussed nowadays is how this outside air pocket can become a way of stacking heat away from the building or creating ventilation schemes. The problem here is not that these aren't good ideas. The problem is the devil in the detail, so to speak. Now the facade becomes a really huge, active, critical component in the performance of the interior conditioned space. And because a lot of people like to have control over what happens at this facade level, the ability to open windows and close windows and control those things, we have many inherent conflicts between what the user desires for thermal comfort at the outside of the envelope and how the envelope needs to perform to create the right conditions inside of the complete building envelope. So these aren't beyond working out, but they do add a huge amount of complexities to the design of these systems. So in your proposal, just a warning, in your proposal of double skin facades, your primary objective should be improving building performance, but not necessarily by just directly saving energy. And then here's some of the basis of that is the double skins facades have been around for a long time. This is now 40 years. The Occidental Chemical Center, this was in Niagara Falls, kind of example of a huge failure of that double skin facade concept. But once again, this is Enclose, the company that makes facades, and they spend a lot of time discussing these double layer facades. So I've put enough negative on it that explore it and make your own determinations about that if you should have the opportunity to explore that. Another thing I wanted to touch on with the glazing systems was this idea of optimizing component design, the idea of getting into the generative design. Why this is important is that we're trying always to reduce the amount of carbon footprint that our buildings put on through their construction and life cycle. And we use a lot of aluminum and stainless steel in the construction of our glazing systems to support aluminum for support frames, steel for the cable systems and the attachment systems. And there's a lot of work going on now to look at ways to optimize the construction of some of these materials to reduce weight. So here we have just the kind of truss systems that we modeled in one of our earlier modules. But the idea of applying some kind of an optimization that comes up with a typology that is almost unrecognizable to us, nothing that we would naturally craft using our own basic engineering principles. But they have been determined by analysis to be structurally superior in their performance. So here we have a large clip over here. This is like we modeled in M2, an attachment clip to hold a facade on. And then a generatively designed, optimized clip system to do the same amount of work but reduce the amount of materials needed in it. And we can take that to the development of our extrusion. So we in our curtain wall extrusion, we came up with a relatively standard shape. But there's a lot of thinking towards the way we can use generative design and even just skill design to remove the mass, as much aluminum as possible, to where it is not doing effective work, and put it in places where it can do. So here we have a higher performing, if we were to look at design A to design B, just to illustrate this a little bit, at design B being stronger but being lightweight. And you'll notice that we've moved our aluminum out to the very far edges of what is a beam, and we're looking in cross section, so that we're putting metal where we need it most and reducing metal where we need it the least. So this can reduce the amount of aluminum and therefore the ultimate carbon footprint of the project, especially when we're extruding miles and miles of this material. And then here's another look at an optimized mullion system, where we have this is an extruded profile, and its shape has been optimized both for aesthetics and efficiency. So when you walk around cities, you'll be able to now, if you start thinking about this, notice all kinds of details in the way glass systems are constructed. So I've got just a few slides of that. So here we have a mid-span support system for a glazing panel, and you'll notice a piece of steel coming out, and you'll also notice that they've encased the steel frame inside the building in an aluminum cladding. And this is typically the kind of issues that you would experience as an architect with little experience in structural steel. You typically don't find beautiful pieces of structural steel like this off the shelf that are inexpensive. Their cost would be almost, many factors over typical steel. And so at that point, when value engineering happens, there needs to be these compromises in order to make the project affordable. In this case, we're using a steel column and then cladding it in steel to give it the aesthetics that we want. Just a nice example of glass, structural glass being used to support the glazing. In this case, note that the glass is attached at the corner, so you don't need to make holes in the glazing system. And all we have is one simple little element at the corner. And then back behind that, this is actually just a really beautiful custom fabricated receiver that accepts these structural elements that are coming into it. Fritting, an important component of the way we work with glass. So this is both curved glass and it has a fritted pattern. These are typically ceramics that are fused to one of the surfaces of the glass. And then this massive amount of structure behind it. So lots of opportunities to look at glass and applications today where we wouldn't have thought about them before, and typically in architecture this would not be your go-to material if you were thinking about making a canopy, unless you'd seen beautiful examples like this. And then also this is just the beautiful structural system that's supporting it, kind of an adaptive column, and then this leaning back of it to both kind of express the way the load is being applied through it. I think this is just really attractive. And in a lot of shall I say public facilities, glass is extensively used, and so here we have the glass back panels, clip systems to support them, massively strong glass elements to resist all kinds of vandalism that would obviously go along with public transportation systems. This is a link to a company that does the fritting, so I put this in. I think it tells you a lot about what happens with glass fritting. And a couple more examples of some glass being used in Chicago as I was walking around. And here's the Jewish, I think it's a museum, but an example up close. You don't notice the fritting until you get up to the glazing area, and here we can see the frit pattern on the glazing system. And then in this case, this is a double wall construction, but there's no intention here to make the exterior wall add to anything more than an aesthetic, because there's no way it's all open. There's no thermal addition to its performance. Apple glass. A good story about the Apple glass is they, as the technology's gotten better, they've actually reconstructed this cube. So you can see that it was, I guess, maybe twice as many panels. It had been then reconstructed with advancements in glass in order to have that more transparent look. Apple's really good about good is really on the edge, so to speak, of the utilization of glass. So here we have glass ceiling systems, glass wall systems, large fin glass structural support here. Look at the massive fins here that are carrying the loads of what are the only steel that appears in it, and these ribs that go along here to support the glass ceiling system. Just an extraordinary use of structural glass. And a couple more views of that. So that cube also, just an idea of this kind of cost of $6 million to take it from 90 panels to 15 panels. And there's a story of someone bumping a snowblower into it, and the need to replace the one panel for $450,000. So, as Apple continues to be one of the innovators, and innovators, it means they put a high demand on it for their phones. That causes companies like Corning to keep advancing the technology and the performance. They talk about Gorilla Glass, which is actually a very flexible, highly durable glass, and they make their way to the consumer level to the architectural level of products, as it can be witnessed in what Apple's doing with their stores. And because of that investment, it's likely we will see continuous innovations in glass in the future. So for our project, we're going to spend a few hours going through and modeling some kind of a structural glass system, so that we can become a little more comfortable with doing the modeling, with thinking about the componentry, with thinking about how it integrates into the architecture, so that you'll be better prepared in the event that you're called upon to participate that in your firm. And this is one of the examples of what we do in the module project M13. This is should be very familiar now. We have a 4-point adaptive system, as we might have used in a space frame. So we have, so we're adding elements in, and then populating a glass curtain wall, a relatively easy system. I also ask you to do I guess a tornado, a structural column system, just to get an idea of applying the ideas we've used to other surfaces that are relatively popular today. So that wraps that up. Thank you for listening.